In mathematics and computing, hexadecimal is a positional numeral system with a radix, or base, of 16. It uses 16 distinct symbols, most often the symbols 0 to 9 to represent values 0 to 9, and E, B, C, D, E, F to represent values 10 to 15. Hexadecimal numerals are widely used by computer system designers and programmers. Several different notations are used to represent hexadecimal constants in computing languages. The prefix 0x is widespread due to its use in Unix and C. Alternatively, some authors denote hexadecimal values using a suffix or subscript. For example, one could write 0 by 2AF3 or 2AF316, depending on the choice of notation. As an example, the hexadecimal number 2AF316 can be converted to an equivalent decimal representation. Observe that 2AF316 is equal to a sum of by decomposing the numeral into a series of place-value terms. Converting each term to decimal, one can further write, each hexadecimal digit represents 4 binary digits, and the primary use of hexadecimal notation is a human-friendly representation of binary-coded values in computing and digital electronics. One hexadecimal digit represents a nibble, which is half of an octet or byte. For example, byte values can range from 0 to 255 but may be more conveniently represented as 2 hexadecimal digits in the range 00 to FF. Hexadecimal is also commonly used to represent computer memory addresses. Representation. Written representation using 0 to 9 and AF in contexts where the base is not clear. Hexadecimal numbers can be ambiguous and confused with numbers expressed in other bases. There are several conventions for expressing values unambiguously. A numerical subscript can give the base explicitly. 15,910 is decimal 159, 15,916 is hexadecimal 159, which is equal to 34,510. Some authors prefer a text subscript, such as 159 decimal and 159 hex, or 159D and 159H. In linear text systems, such as those used in most computer programming environments, a variety of methods have arisen. In URIs, character codes are written as hexadecimal pairs prefixed with %. http://www.example.com/name%20 with %20 spaces where %20 is the space character. In XML and XHTML, characters can be expressed as hexadecimal numeric character references using the notation and hashtag Xcode, where code is the 1 to 6-digit hex number assigned to the character in the Unicode standard. Thus an #X 2019 represents the right single quotation mark. Color references in HTML and CSS and X window can be expressed with 6 hexadecimal digits prefixed with #. White, for example, is represented #FIF. CSS allows 3 hex-digit abbreviations with 1 hex digit per component. #FAR3 abbreviates #FAR33. *Nix shells, AT&T assembly language and likewise the C programming language, which was designed for Unix, used the prefix 0x for numeric constants represented in hex. 0 by 5A3. Character and string constants may express character codes in hexadecimal with the prefix x followed by 2 hex digits. X1b represents the ESC control character. X1b 0 meters. X1b 25 1H is a string containing 11 characters with 2 embedded ESC characters. To output an integer as hexadecimal with the print function family, the format conversion code %x or %hex is used. In the Unicode standard, a character value is represented with U+ followed by the hex value. U plus 20AC is the euro sign. In MIME quoted printable encoding, Characters that cannot be represented as literal ASCII characters are represented by their codes as 2 hexadecimal digits prefixed by an equal to sign equals, as in Esper equals F1A to send, España. In Intel-derived assembly languages and modula2, hexadecimal is denoted with a suffix H or H, FFH or O5A3H. Some implementations require a leading 0 when the first hexadecimal digit character is not a decimal digit, so one would write 0 FFH instead of FFH. Other assembly languages, Pascal, Delphi, some versions of BASIC, GameMaker language, Godot, and Forth use $ as a prefix. $5A3. Some assembly languages use the notation HABCD. Ada and VHDL enclose hexadecimal numerals in base numeric quotes. 16 number 5A3 hash. For bit vector constants, VHDL uses the notation X, 5A3. Verilog represents hexadecimal constants in the form 8HFF, where 8 is the number of bits in the value and FF is the hexadecimal constant. The Smalltalk language uses the prefix 16R. 16R5A3. PostScript and the Bourne shell and its derivatives denote hex with prefix 16 hash. 16 number 5A3. For PostScript, binary data can be expressed as unprefixed consecutive hexadecimal pairs. AA213FD51B3801043FBC. In early systems when a Macintosh crashed, 1 or 2 lines of hexadecimal code would be displayed under the SAD MAC to tell the user what went wrong. Common Lisp uses the prefixes #x and number 16R, setting the variables *read base * and *print base * to 16 can also use to switch the reader and printer of a Common Lisp system to hexadecimal number representation for reading and printing numbers. Thus hexadecimal numbers can be represented without the #x or number 16R prefix code when the input or output base has been changed to 16. MSX Basic, Quick Basic, Free Basic and Visual Basic prefix hexadecimal numbers with an H and H5A3. BBC Basic and Locomotive Basic use and for hex. T89 and 92 series uses a 0H prefix. 0H5A3. The most common format for hexadecimal on IBM mainframes and mid-range computers running the traditional OSs is X5A3, and is used in assembler, place, COBOL, JCL, scripts, commands and other places. This format was common on other IBM systems as well. Occasionally quotation marks were used instead of apostrophes. Donald Knuth introduced the use of a particular typeface to represent a particular radix in his book The Textbook. Hexadecimal representations are written there in a typewriter typeface. 5A3. Any IPv6 address can be written as 8 groups of 4 hexadecimal digits, where each group is separated by a colon. This, for example, is a valid IPv6 address. 2001, ODB8, 85A3, 0000, 0000, 8A2E, 0370, 7334. This can be abbreviated as 2001, DB8, 85A3, 8A2E, 370, 7334. Globally unique identifiers are written as 32 hexadecimal digits, often in unequal hyphen-separated groupings. For example, 3F2504E0 to 4F8941D3 to 9AOC0305E82C3301. Algol68 uses the prefix 16R to denote hexadecimal numbers. 16R5A3. Binary, quaternary and octal numbers can be specified similarly. There is no universal convention to use lowercase or uppercase for the letter digits. and each is prevalent or preferred in particular environments by community standards or convention. During the 1950s, some installations favored using the digits 0 through 5 with a macron to denote the values 10 to 15 as 0, 1, 2, 3, 4 and 5. Bendix G15 computers use the letters U through Z. The Libroscope LGP30 used the letters F, G, J, K, Q and W. The ILLIACI computer used the letters K, S, N, J, F and L. Bruce Allen Martin of Brookhaven National Laboratory considered the choice of AF ridiculous, and in a 1968 letter to the editor of the CACM proposed an entirely new set of symbols based on the bit locations, which did not gain much, if any, acceptance. Soviet programmable calculators 3 to 34 and similar used the symbols -L, C, E on their displays. Digit F was blank. The National Semiconductor MM74C912 displayed O for A and B, minus for C, D and E, and blank for EF. The CD4511 just displays blanks. Verbal and digital representations. There are no traditional numerals to represent the quantities from 10 to 15. Letters are used as a substitute, and most European languages lack non-decimal names for the numerals above 10. Even though English has names for several non-decimal powers, no English name describes the hexadecimal powers. Some people read hexadecimal numbers digit by digit like a phone number. 4DA is 4DI. However, the letter A sounds like 8, and D can easily be mistaken for the TI suffix. Is it 4D or 40? Other people avoid confusion by using the NATO phonetic alphabet. 4DA is 4 Delta Alpha, the Joint Army, Navy phonetic alphabet, or a similar ad hoc system. Systems of counting on digits have been devised for both binary and hexadecimal. Arthur C. Clarke suggested using each finger as an on-off bit, allowing finger counting from 0 to 102,310 on 10 fingers. Another system for counting up to FF16 is illustrated on the right. Signs. The hexadecimal system can express negative numbers the same way as in decimal. -2A to represent -4210 and so on. However, some prefer instead to use the hexadecimal notation to express the exact bit patterns used in the processor. So a sequence of hexadecimal digits may represent a signed or even a floating point value. This way, the negative number -4210 can be written as FFFFFFD6 in a 32-bit CPU register, as a C2280000 in a 32-bit FPU register, or C450000000000 in a 64-bit FPU register. Hexadecimal exponential notation. Just as decimal numbers can be represented in exponential notation, so too can hexadecimal. By convention, the letter P represents times 2 raised to the power of, whereas E serves a similar purpose in decimal as part of the E notation. The number after the P is decimal and represents the binary exponent. Usually the number is normalized so that the leading hexadecimal digit is 1. Example: 1.3det42 represents 1.3de16 times 242. Using the %a or %a conversion specifiers. This notation can be produced by implementations of the print family of functions following the C99 specification and IEEE STD 1003.1 POSIX standard. Hexadecimal exponential notation is required by the IEEE 754-2008 binary floating point standard. Conversion. Binary conversion. Most computers manipulate binary data, but it is difficult for humans to work with the large number of digits for even a relatively small binary number. Although most humans are familiar with the base 10 system, it is much easier to map binary to hexadecimal than to decimal because each hexadecimal digit maps to a whole number of bits. This example converts 11,112 to base 10. Since each position in a binary numeral can contain either a 1 or a 0, its value may be easily determined by its position from the right. 00012 equals 110, 00102 equals 210, 01002 equals 410, 10,002 equals 810. Therefore, with little practice, mapping 11,112 to F16 in one step becomes easy. See table in written representation. The advantage of using hexadecimal rather than decimal increases rapidly with the size of the number. When the number becomes large, conversion to decimal is very tedious. However, when mapping to hexadecimal, it is trivial to regard the binary string as 4-digit groups and map each to a single hexadecimal digit. This example shows the conversion of a binary number to decimal, mapping each digit to the decimal value, and adding the results. Compare this to the conversion to hexadecimal, where each group of 4 digits can be considered independently, and converted directly. The conversion from hexadecimal to binary is equally direct. The octal system can also be useful as a tool for people who need to deal directly with binary computer data. Octal represents data as 3 bits per character, rather than 4. Division remainder in source bases with all bases. There is a simple algorithm for converting a representation of a number to hexadecimal by doing integer division and remainder operations in the source base. In theory, this is possible from any base. But for most humans only decimal and for most computers only binary can be easily handled with this method. Let D be the number to represent in hexadecimal, and the series He-1, H2, H1 be the hexadecimal digits representing the number I1. Hide D mod 16. D 16. If D equals 0, else increment I and go to step 2. 16 may be replaced with any other base that may be desired. The following is a JavaScript implementation of the above algorithm for converting any number to a hexadecimal in string representation. Its purpose is to illustrate the above algorithm. To work with data seriously, however, it is much more advisable to work with bitwise operators. Function toHex var equals d%16 var result if result equals tocha else result equals toHex 16 plus tocha return result. Function tocha const alpha equals 1 2 3 4 5 6 7 8 9 a b c d e f. Return alpha. Caret addition and multiplication. It is also possible to make the conversion by assigning each place in the source base the hexadecimal representation of its place value and then performing multiplication and addition to get the final representation. That is, to convert the number B3AD to decimal, one can split the hexadecimal number into its digits B, 3, A and D, and then get the final result by multiplying each decimal representation by 16p, where p is the corresponding hex digit position, counting from right to left beginning with 0. In this case we have B3AD equals plus, which is 45,997 base 10. Tools for conversion. Most modern computer systems with graphical user interfaces provide a built-in calculator utility, capable of performing conversions between various radices, in general including hexadecimal. In Microsoft Windows, the calculator utility can be set to scientific mode, which allows conversions between radix 16, 10, 8 and 2, the bases most commonly used by programmers. In scientific mode, the on-screen numeric keypad includes the hexadecimal digits A through F, which are active when hex is selected. In hex mode, however, the Windows calculator supports only integers, real numbers, rational numbers. As with other numeral systems, the hexadecimal system can be used to represent rational numbers. although repeating expansions are common since 16 has only a single prime factor, where an overline denotes a recurring pattern. For any base, 0.1 is always equivalent to 1 divided by the representation of that base value in its own number system. Thus, whether dividing 1 by 2 for binary or dividing 1 by 16 for hexadecimal, both of these fractions are written as 0.1. Because the radix 16 is a perfect square, fractions expressed in hexadecimal have an odd period much more often than decimal ones, and there are no cyclic numbers. Recurring digits are exhibited when the denominator in lowest terms has a prime factor not found in the radix. Thus, when using hexadecimal notation, all fractions with denominators that are not a power of 2 result in an infinite string of recurring digits. This makes hexadecimal less convenient than decimal for representing rational numbers, since a larger proportion lie outside its range of finite representation. All rational numbers finitely representable in hexadecimal are also finitely representable in decimal, duodecimal and sexagesimal. That is, any hexadecimal number with a finite number of digits has a finite number of digits when expressed in those other bases. Conversely, only a fraction of those finitely representable in the latter bases are finitely representable in hexadecimal. For example, decimal 0.1 corresponds to the infinite recurring representation 0.19999999999 in hexadecimal. However, hexadecimal is more efficient than base as 12 and 60 for representing fractions with powers of 2 in the denominator. Irrational numbers. The table below gives the expansions of some common irrational numbers in decimal and hexadecimal. Powers of 2 have very simple expansions in hexadecimal. The first 16 powers of 2 are shown below. Cultural etymology. The word hexadecimal is composed of hexa, derived from the Greek epsilon chi for 6, and decimal, derived from the Latin for tenth. Webster's Third New International Online derives hexadecimal as an alteration of the All-Latin sexagesimal. The earliest data tested for hexadecimal in Merriam-Webster Collegiate Online is 1954, placing it safely in the category of international scientific vocabulary. It is common in ISV to mix Greek and Latin, combining forms freely. The word sexagesimal retains the Latin prefix. Donald Knuth has pointed out that the etymologically correct term is centenary, from the Latin term for grouped by 16. Alfred B. Taylor used centenary in his mid-1800s work on alternative number bases, although he rejected base 16 because of its incommodious number of digits. Schwartzman notes that the expected form from usual Latin phrasing would be sexagesimal, but computer hackers would be tempted to shorten that word to sex. The etymologically proper Greek term would be hexadecimal. Used in Chinese culture, the traditional Chinese units of weight were base 16. For example, 1 jin in the old system equals 16 taels. The suanpan could be used to perform hexadecimal calculations. Primary numeral system. As with the duodecimal system, there have been occasional attempts to promote hexadecimal as the preferred numeral system. These attempts often propose specific pronunciation and symbols for the individual numerals. Some proposals unify standard measures so that they are multiples of 16. An example of unified standard measures is hexadecimal time, which subdivides a day by 16 so that there are 16 hec-hours in a day. Key to number base notation. Simple key for notations used in article